quickly record this. So first off, our exam is going to be next Friday. I will be giving you a practice exam. As a reminder, one of the questions that will be on the exam is a question about comparing the big O operations of, the various aspects of linked lists and array lists, and you'll want to use big O to do those comparisons. You'll want to compare the add and remove operations and how they work in linked lists and array lists. You'll want to compare your get and set operations and how they compare with each other, and you'll want to compare your the memory usage of those, which we will go over when we review for that exam. I plan on doing an exam review on the 30th. Okay. So I'll release the practice exam very short, probably today, and then I'll go over it on Thursday, and then on Friday you'll take your exam. You'll have 2 hours to do it. It will be fairly short. It will be online, in the sense it'll be on Canvas. So you're free to use your IDE or whatever. It's just a matter of no going and using Stack Overflow, right? Basically, if you can connect to it on through Canvas, it's okay to use. So that includes my GitHub repository. That includes the YouTube videos that I post. If you need to, you'd have to also open Book and Open Note, right? So you can have this kind of standard resources that you would have to access to, except other human beings, right? Because this is a test of how well you mastered your skills. It will go over, I think, almost exclusively array lists and linked lists. I don't think I'll be including stacks in that. So moving on with stacks, though. So yeah, if you need more time on the Josephus and the solitary encryption, because I did get a couple emails, and I realized I had said it this early. So I'll go ahead and up the time for it. I think what was going on is that when we were doing this in over the summer, and people were had a bit less access to me. This was or not summer, but spring when we were online, and fall I had it for a longer due date. So I'll probably have to, and then okay. Regardless. Point being is that we have these accessed, and now we'll do them. And now we've got the maze exercises to do. So the maze solving isn't actually too difficult. It is once you get it understood. It should also be fun. I created this one. This is one of those where I created it on my own and didn't really have to take any inspiration from anybody else's prior assignment. So this is all code that I wrote. Let's see, did I ever fix maze grid panel? No. No, did I ever fix maze? Yes, I did. Okay, so this will basically create a maze for you, and the goal is to automatically create a path from the end of the maze to the beginning of from the beginning of the maze to the end of the maze. Now I like this assignment because I like mazes. Mazes are very interesting puzzles. They also feature heavily in video games in some kind of form. And Wikipedia's got actually a great videos about maze solving algorithms, which are very similar to your maze generating algorithms. Okay, so first and foremost, and apologies for people watching this later on here, there is a couple, depending on the maze you're encountering, there are some simple rules you can use to solve a maze. The simplest one is the right hand or left hand rule, where I've entered the maze, the exit's over there. It's on the same wall, which is kind of a requirement. The same wall being is that it's not on an inner wall. You're not trying to get to an elevator at the center that's going to lead you out of the maze. You're in a box, and the entrance and the exit are on the sides of the box. Tap your hand on the wall, and don't let go at any point. You'll eventually get out. And what this will do, this will trace a route through the maze. And you can see basically if we consider these tables to be walls as well, I'd just basically weave in and out until I got to the end. Okay? But this only works on some kind of mazes. That doesn't necessarily work. But here's an example of that right-hand rule on Wikipedia. And we can see basically that we're just grabbing this wall and we're following the wall and we eventually get to the end. Not a very complex maze, but there are kind of ways to do that. So wall following is pretty good. There are other ones, but the way we're going to be doing is depth first search, where basically, and what depth first search means is that basically we go down a path and we follow that path as far as we can until we get to a dead end. Now in real life, this requires two tools that we're going to be using in the maze that are similar to what we're doing, to the tools we have on the computer. So let's go and look back to a bit of Greek mythology, which is the labyrinth. All right. Okay, so the labyrinth, right? For those of you who remember Greek mythology, was this maze created by Daedalus for King Minos, which he threw to imprison the Minotaur, and then he'd throw various sacrifices into it. Theseus, one of Zeus's many illegitimate offsprings, because basically that is what all Greek mythology is, just a bunch of Zeus's illegitimate offspring going on adventures. So anyway, Theseus basically slew the Minotaur with the help of Ariadne and her string, and there's a good picture of it over here. See Theseus in the Minotaur's labyrinth. Now, notice over here the string. Why is this important? Because it allows him to go backwards from where he was. It allows him to backtrack. It allows him to not get so lost in this curvy maze. Now, technically, what we need if we're doing this labyrinth is that we need basically, he's got all he needs. He's got the string, and more importantly, he's got that sword, but not for the reasons you think. It's not necessarily for killing the Minotaur here, but that sword's useful because he can make markings on the wall with that sword, assuming it's mystically sharp and all. Hero, you gotta have a magic sword. For us, that basically we can recreate that with chalk, using chalk to mark our trail, and then what we do is, and now why is this important to make markings if you've got that string? Well, let's say I go and I hit a dead end, right? So I gotta back up to where I can make another choice, which is here, right? I can go this way instead. And so what I'll do is I'll make some kind of mark over here to say, I've already gone down this way, so I'm going to go trying this way, right? I went this way, I backtracked. So if I get to a dead end this way, I need to know I don't want to go this way again. Otherwise, we're going to get into an infinite loop, right? So we can accomplish this in our program by using just color. What I typically suggest so in our function, we have I created this very useful function for you, which is visited, which returns true or false. Okay? And basically says if the square that you're on has a color, so basically your maze is divided into a bunch of square cells. Because that's the way mazes are always generated. It's a bunch of square cells. The easiest way to just make a grid for the maze. And so what you do is that basically you say, okay, given the row column coordinates of the cell of where the square in question is, I ask what color is that set to. Now the cell is just a piece of graphical It's a little graph you can see. It's a little window. The UI is something I've done. It's very simple. Really all you need to know is basically that you can get the background of the cell and you can set it by doing background.getColor, and as you'll see, background.setColor. So all I do is I get the color, get background, and I ask, hey, is it white or is it red? If so, it's unvisited. That allows you to mark any other color. Why red? I use red for the ending. I use red. So if you get to a red square, you know you've gotten to the exit. That's how I know if you've gotten out. All right, so, and notice over here that when I start the maze, when I create the maze, I set the background, I set the starting point to green, and you can use green if you want to, that's fine, for marking trails. And then I set the background to red. Okay? So I set the colors of the squares, and then I can just check, hey, have I been to this place yet? So that's us marking our places. We can just simply, if we need to back up, we can. So how the heck do we do that? And how the heck do I move through this maze? Well, your movement is done through the stack. That represents both your rope and your current position. Your current position's on what the top of the stack is. What the heck is a stack for those of you who haven't watched the videos yet? A stack is a dumb linked list. But dumb but powerful linked list. It's essentially, if I had to simplify it, it's a linked list where the only operations you can do are on the head of the list. So you can only look at the top item of the list, you can only look at the head of the list, add to the head of the list, or remove from the head of the list. That's it. Oh, you can also check if it's empty. That's kind of useful too. But basically your current position is going to be the head of the list. And then if you want to move to your next position, therefore, you just push or add a new item to the stack. Make sense? And if you need to go back on the stack, you pop from the stack to back up. So basically you can just do stack.peek, that's the term to look at the top. Stack.peek will show you the current cell because it's a stack of cells. And you can look and check what color it is. And to see if you've been there before, if you need, so you can peek to get its position. And you only really care about its color if you're deciding where you're going to go next. Okay? So, one more useful thing. I generate this maze in a very specific manner. Okay? And that's so that it creates a... here, I can go ahead and download these things and boot up IntelliJ. Okay, so let's go ahead, maze grid panel, cell. I generate this maze in a very specific manner, which is to be very easily solved. It creates a very easy to find solution. Okay. So why did this one go into here, but the other ones went to the desktop? Okay, so copy. Okay, close. Project. Whatever, I'll just drop it in here. Copy paste is not allowed during indexing. All right. Pause the indexing. Nope. Okay. So let's just look. So what the maze does is that it will set up a 5x5 maze, which isn't very interesting, but it's easy enough to solve at the moment. You can change this into like a 50x50. Anything above that will start to get really dumb, so to say. Maze grid panel, this basically is the window that's going to this is basically the frame that holds the maze. And when I generate this maze, basically what I do is I've got a grid with a bunch of squares, and they're all got their borders set up. And what I do is I choose a is that I flip a coin and I choose a wall to either to remove the north-south wall pair or the east-west wall pair. The extra credit is to generate a maze, by the way. So if you want to use depth first search to generate a maze with more curvy paths, which is a lot more fun to solve. But all right, so now it's done. Okay, so now I can run it. Okay, so we'll want to run the maze, which extends the J-frame, which just means that the maze is a window. So then you've got a panel inside the window frame. Okay, class not found exception main. Why? Cannot find oy vey. Okay. Why does it not want to find maze? It's right here. It's not in the okay. Or okay, so fine. New project. Next. Sorry about this. Maze. This window. Refactor. Oh, yes. Okay, let's move you guys into SRC. And now okay. And there you go. There's our 5x5 maze. Not particularly interesting. Let's go ahead and up it to 10. Yeah, let's go with 50 by 50. Why not? So it generates it. And there's our maze. And there's a very specific path that you can basically the path is always going to look like a squiggly diagonal. So here, basically, you can follow my mouse and you can see that there's basically a path you can get out that just simply follows the diagonal. This column over here in this row is always clear. This is just basically an easy way to guarantee that there's always going to be a solution. So your final, so again, how do I move this thing? Well, for the what you're going to want to, there's pseudocode in the write-up for this. And basically, if you follow the pseudocode, you're going to be fine. But what you're going to do is that you're going to want a while loop. Now, what I'm going to do here is not put in a while loop because the while loop, that's something you should do last, oddly enough, to figure out, like, okay, what is my terminating condition now that I've got the maze going? So instead, before I figure that out, I'm going to do a for loop. Basically, I'm only going to do a certain number of steps. And here I'm going to kind of demonstrate how the movement works. What I'm going to do is I'm just going to move south. I'm going to move my square south. So what I'm going to do to move south is I'll just simply do stack dot push. Okay, and if I want to move south, so I've got this maze array here, which is like, you know, the stuff. Which is the array of all the cells. So if I want to go south, well, here what I want to do is first I want to get where I currently am. So cell current is equal to stack dot peak, right? Get my current, stack dot push, maze, and it's going to get current dot row, current dot column. That would get the exact same cell though. So here's the thing. I want to move down. So what do I do to move down? How do I what do I need to adjust to go down, to go south? Yes. Increase the row by one, which is a bit. It feels so wrong, right? Because you're increasing the row by one, but we were like, wait, the first coordinate's the x coordinate, right? No, this is row column. It's like matrices. So, and then you're increasing by one because this top left corner in an array is 0, 0, right? You're kind of working in quadrant 4. That's always the way it works in graphics. You're working in that weird negative y but positive x quadrant. Okay. So stack.push, and then what I'm going to do is also, I'm going to make sure to color current.color to dot background, let's see, set background to a color. And to do a color, you just simply say set background color dot, and I'm going to go with blue for my path, okay? Color dot blue. Okay? And you'll see I've moved down 10 spaces. Now, a couple things. Now, one of the dangers that you're going to have is going out of bound. But fortunately, you don't have to check your coordinates to see if you're going out of bound. Instead, this entire thing, and the reason I'm running this, is surrounded by a wall. So there's a wall here, a wall here, a wall on the bottom, and a wall on the west side as well. So what you're going to want to do is ask, basically, is there a wall? So, and the way you do that is the cells have a bunch of booleans, that tell you whether or not there's a wall. So you'd simply ask, does this position, dot east wall, is that true or false, right? If it's true, there's a wall there, so you can't go that way anyway, so don't try to, or actually what you do is you'd ask your square, because your square would have that wall. So you'd ask, hey, current dot, east wall, west wall, and if there is one of those, if there is a wall, you cannot go that way, right? So you look at your square and you can figure out which ways you can go based on what walls you have. Okay. Then once you've got this adequate, what you feel is an adequate amount that's going to solve the maze, you can figure out what the ending condition is. Okay, because it won't give you partial progress. It will give you it will only show you the end result. Okay? So, any questions about this one? It's not as hard as it looks. That's actually a very common refrain I'm going to have in this class.